hope everyone had a wonderful, wonderful break and had a chance to be with family if possible. I had the wonderful experience of taking a granddaughter to the temple for her first time as she gets ready to go to Milwaukee on her mission. And then the rest of the time we look for very heavy winter coats. So it was a good family trip. As you can see, we did quite well on this midterm. Because of the break is pretty old news. This is where we've been. But there were 12 perfect scores. We had 116 scores that were in the A category, 122 that were in the B category. And so all in all, things went very well. Now I posted a video of me going through each problem in detail and showing the answers to those questions. So if you didn't end up in that A category, you might want to go and review those questions that you missed. Let me just point out that the final exam is not really a final. It's the 5th midterm, and it covers this new material on waves. And so there won't be anything on the previous material. It will just be on the new material. Yes.
Yeah. I'm not there.
The what? The last exam, the final, is at the testing center, and it's from the 13th till the 18th, the entire week.
Doing better.
Okay. Let's. Sure, we're all sharing our stories about Thanksgiving. Let's settle down with opening prayer. Would someone be willing to offer that for us? Thank you, sir.
Heavenly Father, we thank you for this day. We thank you for this opportunity we have here. Ask more about it. For this opportunity, we have to be able to be studying here at BYU. We ask you to please bless us to have the Spirit to be with us, that we'll be able to go forward and learn. We ask that you please bless us to be able to have a good rest of the semester and prepare for our finals. We say things.
Amen. Thank you. Thank you very much. Okay. Let's see if we can. There we go. We've arrived at the best part of this material, standing waves. I just love standing waves. Standing waves are the foundation for music. And everything I know about music, you could dance on the head of a pin. What I wanted for my, I think it was my 10th birthday, was to be able to quit piano lessons. And my parents gladly gave me that because I was no good. Today we're going to talk about transverse standing waves, the type that would happen on a violin or a guitar, any strings, wire. And on Thursday, we're going to talk about longitudinal standing waves, primarily those that happen in wind instruments like an organ pipe or a flute, something like that. Now, let's start by taking attendance, see who came back from Cancun. Okay, now you can click.
Judge so much more. So distracted me.
You always want to click several times, make sure that your click gets registered.
Next. Even I kind of like.
I will point out that last week on Tuesday, we only had 150 clicks. We were, a lot of us gone. Okay, last call. Okay, we're here. Some of us are making the Doppler shift way, way more difficult than it is. All you need to know about the Doppler shift is that if you're going towards the source of the sound, or the source is coming towards you, the shift is to a higher frequency. If that source is making 400 hertz, you're going to hear something higher than 400 hertz. That's the shift, up. And if that source is going away from you, or you're running away from the source, the shift is going to be down. If it's making 400 hertz, you're going to hear something lower than 400, 390, something like that. And that's the shift. Now, how big that shift is has absolutely nothing to do with how close the source is to you. It has absolutely nothing to do with anything other than velocity, relative velocity. If you're going 60 miles an hour towards that source, you're going to hear a bigger shift than if you're going 30 miles an hour towards that source. And that's it. That's it. Everything that you need to know about Doppler shift was right there. Okay. Again, we'll have a chance to review some of these ideas next week as we get ready for that last exam. Next Wednesday, I've reserved this room at 7 o'clock in the evening. That's right before the reading time. Thursday next week is the reading period. And so the Wednesday before that, I will be here at 7 o'clock. We can go over some of those ideas. What we're going to talk about today involves the idea of resonance. And I think we all have a gut feeling for what resonance means. There are certain frequencies at which systems just want to vibrate. The classic example is when you're pushing your kid brother or sister on a swing. You know that if you want to get your kid brother or sister going as high as possible, there's one frequency that's going to make that happen. And if you're pushing at any other frequency, the kid's just going to get mad at you. Okay? If you're always pushing at the same frequency that they're going back and forth, you're going to put more energy in each time you push. And they're going to go higher and higher and higher until you get in trouble with your mother. Okay? Now, if you're pushing at a different frequency, sometimes you're going to be pushing when they're going away from you, and sometimes you're going to be pushing when they're coming towards you. You're just going to make them mad. That's not going to put energy into the system. Okay? Now, the classic example of resonance is the Tacoma Narrow Bridge. This bridge was built in such a way that when the wind picked up, and it wasn't a stiff wind, it was 40 miles an hour, but you know, that's hardly a hurricane. One morning that wind just got that bridge just rocking back and forth, and eventually the amplitude got so big that it fell apart. Okay, it fell apart. Now, most of you are going to, at some point in your career, see a movie of this, so I'm not going to show you the movie right now. So let's talk about a resonance phenomena called a standing wave. Now, a regular traveling wave is like this. Oh! That disturbance went across the room, assaulted your eardrum. A standing wave is more like It's just a vibration, okay? And so I'm going to create a standing wave here. And hi. Hello. Now, if I just start wiggling my hand, the thing is fighting me. And you see it's tugging on my hand. But if I do it at the right frequency, it doesn't fight my hand. And each time that I slightly move my hand, I put more energy into the system. And we would call that the first harmonic. Now, if I move my hand faster than I have been, it starts to fight me again until I find just the frequency where it stops fighting me. And now you see I call them footballs. There's two footballs now, and we call that the second harmonic. Now, if I wiggle my hand just a little bit faster, it starts to fight me again until I find just the right frequency that we call the third harmonic. And now you see that there are three footballs. I'm not sure whether I can do the fourth harmonic or not. Let's try. Come on, Greg. Simply amazing. Oh, man. I love my job. Now, let's talk about the resonance that's going on. By resonance, we mean there's just certain frequencies at which this thing has big amplitude, and the other frequencies, not so much, okay? And every system has these resonant frequencies in it. I used to drive a 1979 Chrysler Cordova, and that thing, when you went down the freeway between Bozeman and Belgrade, it would hit the pavement brakes at just the right frequency that this car wanted to rattle apart at, you know? And so if you were going 55 miles an hour, it was just going to rattle your car apart. So you had to go faster or slower to avoid that resonance. Now here the resonance is caused by adding energy at just the right time, kind of like pushing your kid, brother, or sister on the swing. If we start with, this is my hand, this is the spring, and I send a pulse down, and because it's fixed over that end, it's tied to the table, the reflection is going to come back on the bottom. And then when it comes back to my finger's not moving hardly at all. And so that's like a fixed end. And so now what's going to happen is that it's going to flip again. So when this hits my hand, it flips back up. And if I'm sending another pulse at the same time that the reflected pulse is bouncing off, they add together, okay? And if I keep on doing that at just the right timing, the amplitude gets bigger and bigger and bigger. Now, what is that timing? Well, if the length of my spring is capital L, and if the speed of that pulse is V, and we have a formula for the speed of pulses on springs, don't we? What was it? Square root of tension over the mass density. The mass density is fixed. Once it comes from the factory, that's a number, okay? But the tension, I can change that speed by making it tighter. I can make it go slower by making it looser. If I change the tension, I change the speed, okay? Now, what I want is how much time it takes for that pulse to go down the length of the spring, bounce and come back. And how long would that be? Well, if you wanted to know how long it took to get to Denver on a road trip, you would take the distance you were going to travel, say 400 miles, and divide by the speed that you were going to be going. say 50 miles an hour. And then that time would be 8 hours, okay? That's just the beginning of the semester right there. Now, we are going to be most interested in the frequency. It's frequencies that we talk about rather than periods. And frequency is just 1 over the period. And so that's just going to be the speed divided by the total distance, which is 2L. Now you're going to see that quantity a lot. We're going to see that over and over again. You just will give that a name. Call it, I don't know, Charlie. That's a 1 Charlie. Okay, 1 Charlie. Okay. Now, I was only able to get to the 4th harmonic because I'm human. So now we're going to get rid of the human and replace it with a machine. And what I've got is a string which is tied down here. And I've got just a jigsaw that's going to go up and down, but not very much. This will be a node. We call it a node where there's no movement. And we call it an anti-node where those footballs were, where there's some maximum movement away from equilibrium. Now, right here, it doesn't go up and down very much. It's what we call a quasi-node. It's like my hand wasn't moving very much. We treat it as if it were a node. Now, let me turn on some lights here. If I okay, something like that would be the 1st harmonic frequency. And then it's just kind of nothing until I get just the right frequency. And now what you should be seeing, let me pull it back so these people can see. What you should be seeing is 2 footballs, okay? Now I got a little swirly going on there when I move the system. Okay, there, do you see 3 footballs? Four footballs? 5 footballs? I can't hold it much longer, Captain. Okay, now I'm going to take it to the 3rd harmonic. Now, folks, I'm going to turn on a strobe light. And there have been some documented cases where a strobe light has kind of triggered an epileptic seizure. And so if you know that you're prone to that sort of thing, you might want to not look at the strobe, okay? So could you turn off the sorry. I'm slowing down time. Okay, and what you're seeing there is that when one football is going up, the neighbors are going down and vice versa. Okay? And what I'm doing is just slowing down time by only looking every time the light flashes. And let me turn that off. Okay. All of you can open your eyes now. Now, so these standing waves, it turns out, satisfy the wave equation. And remember what the wave equation is. It's the velocity is always equal to the wavelength times the frequency. That's the F equals ma of this part of the class, of the waves part of the class. Well, if a standing wave stands, if it doesn't go anywhere, why do I have velocity in an equation that governs a standing wave? Well, to answer that question, I'm going to look at this this wave machine. I've got my helper here. She's going to clamp that last little bar, and I want you to watch as I send a wave down from left to right. You'll see a traveling wave, and then when it bounces and coming back, you'll have one wave going to your left and one wave going to the right, and you'll see that we get a standing wave. Okay. Now it bounced, and now I've got the standing wave. Okay. So I've got a movie of that. Now, folks, this movie looks very, very primitive, but it was far ahead of its time. This movie was created in 1992, back in the before days. And it was made by a grad student of mine who dropped out of school. Okay. He dropped out of school, not because he couldn't hack it, but because he was spending all of his time on this new fad that I told him was going to go away, computers. Okay, that's all he wanted to do was computers. So he dropped out of school, went to Silicon Valley. Now he is wealthy enough to own several nations, and but he doesn't have that degree. Okay, but at the time, the software for making movies did not exist. And so he made this just pixel by pixel, and it was very much something at the time.
Here we show the superposition of two oppositely propagating but otherwise identical sine waves. The blue wave propagates left to right, whereas the green wave right to left. The bottom trace shows their sum. The addition of these two waves result in a wave that oscillates but stands still, hence the name standing wave. The dashed lines are positioned at nodes of the standing wave, points that do not oscillate. These represent, in the case of, say, an acoustic cavity, rigid walls, or in the case of an optical cavity, reflecting mirrors.
So a standing wave is really two traveling waves that are identical to each other. It's just moving in opposite directions. And that's the summary here. It arises from superposition of two identical waves traveling in opposite directions. It only happens at certain frequencies. It's a resonance phenomena. The nodes are the points that are not vibrating, are not moving away from equilibrium. And the antinodes are where you get the most displacement from equilibrium. I call those the footballs. Now, the name of the game with these standing waves is to find those resonant frequencies. What frequencies is this system, whether it's a guitar string or some other stringed instrument, what frequencies will it resonate at? Now, we call this the first harmonic, the first resonance, if you will. And sometimes we also call it the fundamental frequency or the lowest frequency that will resonate. And in this case, we only have one football, okay? And that football, what you should be seeing, like with the strobe light, it goes down and then it comes up and then it goes down and then it comes up. And what you're seeing is different locations at different times. Okay, now, what's that frequency? Well, I can't see a frequency, but I can see a wavelength and I can draw a wave. And so that's the technique that I use to find these frequencies. I draw the wave and then I use the wave equation to find the frequency. Okay, we'll practice that. We'll practice that. So that's a node, that's a node, that's an antinode. And here's one of the things you need to have in your toolbox. It takes 2 footballs to make a wavelength. Turn to your neighbor and tell them how many footballs it takes to make a wavelength. Is that always true or just sometimes true? Always true, always, every stinking time. 2 footballs make a wavelength. So what I've got here, I've got half a wavelength. I've only got 1 football. Okay, so if I want to know how big the wavelength is, well, if the length of the string is half a wavelength, then that means the wavelength must be twice the length of the string. Okay, and that's the longest wavelength that will resonate. Now, if I go to the next allowed resonance, we call that the second harmonic. Now I have 2 football. Okay, and you see that when this one is at position 1 over here is down. When this one's up, that one's down. When this one's down, that one's up. Okay. Well, again, 1 football. I got 2 antinodes here, 2 footballs. If I want to find a wavelength for this standing wave, 1 football is half a wavelength. And I've got 2 of them. Okay. And that means the length of the string is just my wavelength. And if I look at that relative to my first wavelength, you see it's half as big. I fit twice as many footballs in the same length. The footballs have to get half as big. Does that make sense? Now, if I go to the third harmonic, the next allowed resonance, well, now if I look for the wavelength, 1 football is half a wavelength, and now I've got 3 of them, okay? And so if I write that another way, it's just 1/3 of the original wavelength, which was 2L. Now again, it just makes sense. I'm now cramming 3 footballs in the same space that used to be held by 1 football. My footballs had to get 1/3 as big. Now here's the takeaway, okay? If my wavelengths go from the fundamental wavelength, the 2L, to half of that much, to 1/3 of that much, to 1/4 of that much, if I use the wave equation, the grand high 1 equation to rule them all and in the darkness bind them, the speed stays the same. That doesn't change. So if this wavelength gets half as big, 1/3 as big, 1/4 as big, the frequency has to compensate. We get the fundamental frequency, the first harmonic, and then twice that frequency. If the fundamental frequency is, say, 12, the next frequency that's going to resonate would be 24, and then 36, and then 48. Okay, because that's what satisfies this wave equation. Now, you see what I did there? I do pictures of what the wave looked like. I figured out how big the wavelength was, and then I use this formula to find out what the frequency was. Now, there's a little bit of a wrinkle, and that is that we talk about waves in the physics department, and they talk about waves in the music department, but we talk about them with different language, okay? Whereas we would call this the first harmonic, the second harmonic, and the third harmonic. They would call this the fundamental frequency, the first overtone, and the second overtone. Now, I'm not saying that someone's wrong. I'm just saying that we're right, okay? Now, did any of you go on a mission to Germany? Raise your hand. Thank you, sir. Okay. So when you're in Germany, if you're wanting to visit someone that is on the first floor, do you have to use stairs? Yeah, you do. Because in Germany, the first floor is one floor up. Okay. What do they call the ground floor? The Erdgeschoss, the ground floor. Okay. And so it would go ground floor, first floor, second floor, third floor. Whereas in America, it's first floor, second floor, third grip. Hi, guys. So it's just a different way of naming. Okay. The Germans aren't wrong, they're just different. Okay. Now, we often in the physics department also call this the fundamental, but we would never call this the first overtone. Okay. And that's because we would like to use a formula where we would like to say that the nth harmonic, the third harmonic, is 3 times the first harmonic. And the fourth harmonic is 4 times the first harmonic. We would like to use that simple formula that the nth harmonic is n times the first harmonic. Check that your neighbor's on the bus, people. I know that more than one person went to Germany on their mission. People are hiding your light.
It's not amplitude. You don't get like back. That's the harmonic that evidence is the principle that drives.
Okay.
Now,
Let's look at a sample problem. A string is stretched between 2 fixed supports, and it sets up a standing wave with 2 nodes between the ends when driven at 240 hertz. We first of all want to draw a picture of the standing wave pattern. Then we want to find the fundamental frequency, and then we want to know at what frequency will the standing wave have 3 nodes between the ends. So let's give ourselves some space. Okay.
In the end?
So the first thing we want to do is draw that standing wave pattern. We're told that it's fixed at 2 ends and that there are 2 more nodes in between, and those have to be evenly spaced. So those would be nodes. We would then have the antinodes in between. Okay, and that's what the spring or string would look like at one instant in time, say noon, and then half a period later, it'd look like that. Okay, and it'd just go from the blue to the red, blue to the red, like that. So, which harmonic is that? Yeah, that's the third harmonic. And we're told in this problem that this wave pattern happens at 240 hertz. We also know that the third harmonic is 3 times the first harmonic. And I know that 240 is 3 times 80. I just remembered that from when I was young, okay? And so that tells me that the first harmonic, the fundamental frequency is 80 hertz. That would be the lowest frequency at which this string or spring would resonate, okay? Well, what frequency would cause 3 extra nodes in between the ends? Well, now what I'm going to get
120.
is 3 nodes in between. And that means I'm going to have 4 footballs. And it would look like that. And then a little bit later, like that. And so that is going to be F4. And I know that F4 is going to be 4 times F1, or 4 times 80 hertz, which would be 320 hertz. Check with your neighbor. Make sure your neighbor thought that problem was easy.
Yeah, I was just seeing if you guys.
Are there questions?
The test. Out on the tests. I actually played
Okay.
crazy.
Now, you've come to expect that just when I get you feeling good about yourself, I pull the rug out from under you, okay? And that's what we're going to do right now. We're going to find another flavor. It turns out, in some states, you can create music by clamping a hacksaw blade to a post and vibrating it. You know, you can actually play music at some weddings this way. Now, the question is, if I do that, what would the lowest 2 harmonics look like, and what frequencies would they have? What would the wavelength of each be? Now, if I think of that as the post, and I clamp that hacksaw blade there, we have to identify what's going on at the ends. We call these boundary conditions. What happens at the ends of the system? Right here where I've clamped that to the post, is that going to be a node or an antinode? That's going to be a node. It's not moving. It can't move. It's clamped. But the free end is always going to be an antinode. And the lowest frequency, the fundamental frequency, F1, is always going to have the longest wavelength that will fit these boundary conditions. Now, the longest wave that'll fit between a node and an antinode is one that goes straight there without any more nodes in between. That is the fundamental wavelength. And from that, I can find the fundamental frequency. Now, how many footballs do I have there? Shout it out. 1/2. How many footballs does it take to make a wave? 2. Okay. So what I've got there is 1/4 of a wavelength. And so now you see that the wavelength of the fundamental is 4 times the length of the system. Now, before, when we had the ends the same, when we went from a node to a node, we started out with twice the length of the system. But with this system, it's 4 times the length. Now, we call that the fundamental because it's the lowest frequency that will resonate. If we look at the next allowed resonance, the next frequency that will give me a loud booming sound. I still have a node here. I still have an antinode there. But I have to add another node and another antinode. Every time you go from one resonance to the next, you have to add one whole football. And so now, how many footballs do I have? I have 1.5. But I'm going to call that 3 halves. Does that offend anyone? No. 3 half footballs. I have tripled the number of footballs that fit on that same length of the hacksaw blade. What does that tell me about the size of my footballs? If I fit 3 times as many in there, they have to get 1/3 as big, okay? And sure enough, when I look at that wavelength, it's the size of the fundamental wavelength divided by 3. And if I went into the next allowed resonance, I would have to add another football. And now I would have 5 half footballs. I would have 5 times as many footballs as I started with. And so now my wavelength of my footballs would be 1/5 as big. So what you see is that I went straight from the first harmonic, the fundamental, to the third harmonic. The second harmonic doesn't exist on this system where I'm going from a node to an antinode. Now, this is something that crosses boundaries. When we talk about organ pipes on Thursday, we're going to find the same thing happens. When the ends are the same, let me just show you here. When the ends are the same, we get all the harmonics, F1, 2, F1, F2, F3, F4, F5, F6 to infinity and beyond. When the ends are different, I just get the odd multiples. I get F1, F3, F5, F7, F9, F11. Check on your neighbor again. Do a buddy check. Yeah. That?
They're the same.
Oh, okay. What do I mean by ends are same or ends are different? If the ends are the same, I've got a node at one end and a node at the other end. Or we're going to see on Thursday an example where I got an antinode at one end and an antinode at the other end. If they're both either the nodes or both antinodes, I get all the harmonics. If they're different, I've got a node at one end and an antinode at the other end. Okay? Now, every system, like I mentioned before, has these standing waves. But when the system is more complicated than a straight wire or string or spring, those standing waves can be more complicated in shape. And indeed, I've got here a 2-dimensional sheet of metal, and I'm going to just vibrate it at different frequencies. And I've put some salt on here to kind of show where the nodes are. This thing's going to start bouncing, and it's going to send the salt to the places that aren't moving, the nodes. And now instead of those nodes being a single point, they're lines. So let me, okay, that's looking down on this plate here. Okay. Now, I'm going to let's see if we can find some other frequencies. Oh. Is that cool or what? Do they do anything like that in your chemistry class? No. Okay. Probably bothers you, but I can't hear it, so I'm fine. Now, just in case that didn't work, I included this. All right. It is music. Okay. Music. Okay, we have an old exam problem. Oh, if I could get help from Sam. Thanks for always volunteering. Good of you.
You don't have to.
I have one of those.
Like anything important though. I helped Denise pick up, the reason she called me to work so I can help her out. Present from having.
This is why I don't go with.
Oh, that's.
Especially when they don't tell you what they need you. I'm like, what do you need? And they're like, just come in.
Yeah.
And then stuff just tell me about. Yeah, it's true. You know, I shouldn't complain, but and then stuff tell me about like a new man. So yeah, apparently the other guy wasn't interested. He was just nice because he's heard it.
I feel like he might be going, but he didn't like six in there.
Classic minister. I feel like it's like he's.
Raise your hand if you still need one.
Real. Like who you ministering to? I texted them. Oh, no. On my.
Here.
I'm a dog.
Oh, not if it's.
It
didn't work.
Oh, what?
Yeah, exactly.
Oh,
An experiment.
okay.
I was able to do both.
Yeah, I can help you.
Does everyone down here have one?
Like, I'll send one.
Thank you.
I think it's gonna go.
Yeah, 'cause she's doing some like.
Okay,
He also wants me to do like. I was gonna grow. So.
in this problem, we,
So you know how much I like you, but I.
in this problem, we have a mass, 30-kilogram mass that is at the end of this wire. And that wire goes over a pulley and it's attached to a ring that is both massless and frictionless. This post here has no friction. And so the first thing we want to do is decide what kind of a system this is. Is this a system that is the ends the same, that has all the harmonics, or one that has ends different? Now we set up the resonance by tapping on this mass, by essentially wiggling that mass a little bit, just a tiny bit. And the question is, what kind of system is this? Ends the same, ends different, or I'm here, but I wish I were skiing. Okay, now you can click.
Thank you.
Now.
Thinking like.
Oh, yeah, that's.
Okay, last call. Okay. Okay, ends are different. That is the correct answer. Where the string goes over the pulley, because of the size of this mass, that's not moving anywhere at all. Okay, that's not, so that's a no. Because this is a free end, like the free end of the hacksaw blade, this is going to be an antinode, an antinode. Now I'm gonna use this document camera to solve this problem here. We're told that the mass is 30 kilograms, and we're asked to find the tension in the string. Well, that's just an old school problem that we've had forever. We just draw a free body diagram for the block, and I've got the weight of the block, which is going to be 300 newtons, and I've got the tension by the string on the block, and the block's not going anywhere. Yeah, it's vibrating a tiny bit, but the acceleration is very small, and so that's going to be 300 newtons. Now, what is the wave speed on that string? Now, folks, when we talk about speed of a wave, we have several formulas. We know that this formula always works, always, always, always. Whether it's a traveling wave, standing wave, transverse wave, longitudinal wave, it don't matter. That always, always works. Now, for a transverse wave, we have another formula, and that is that the speed is equal to the square root of the tension by the string on the block divided by the mass density. Okay? Now, if it's a sound wave, we have an even simpler formula. The speed is 343 meters per second. Full stop. Okay? So those are the two types of waves. Transverse uses this formula. Longitudinal would be a sound wave, would use the 343. Okay? Now, I know what the tension is. I need the mass density. Well, the linear mass density, remember, was the total mass divided by the total length. Now we're told that the whole 3-meter long string has a mass of 40 grams. So that's 0.04 kilograms. And that's the mass of the whole 3 meters of length. Now, not all of the 3 meters are wiggling. Yes.
343 sound.
We just measure that. That's the speed of sound in at room temperature. And so it's not that we derived it, it's just we made a sound and we measured how long it took to get the spring go. Yeah.
You have those formulas on your test.
God. Of course. I love you. I give you everything you need. Okay?
I guess.
Okay, so this turns out to be 0.013333 kilogram per meter. And so if I plug that back into this formula, I get the square root of 300 newtons divided by this 0.01333 kilograms per meter, and that gives me 150 meters per second. Are we all on the bus? Okay. Now, in part C, we want to draw, sketch the lowest frequency. Now, again, I can't see a frequency. I can't draw a frequency, but I can draw a wave, okay? And I know that if this has to be a node and this has to be an antinode, the lowest frequency is going to be the longest wavelength. How do I know that? By this equation up here. If V is always 150, the lowest frequency, the smallest frequency, is going to be when I have the longest wavelength. Okay? And the longest wavelength that goes from a node to an antinode is half a football. Okay? Now, the next allowed frequency, remember when I go from one resonance to the next one, I have to add one whole football. And so now what I'm going to see is three half footballs. Okay, there's one half, two halves, three halves. Okay, so here I have a half of a football, and here I have three half footballs. Now, folks, I'll warn you, nobody else on the planet calls those footballs. And if you call them footballs in some other context, you're at some party years from now and you're, oh, look how many footballs there are in that standing wave. People are going to ridicule you, okay? But in this class, we can talk about footballs. And that's because I have a formula that no one else uses because it sounds silly. And that's this formula here. The number of footballs times lambda over 2 is always going to equal the length of the system that's oscillating. Now, in this case, the length of the string that is oscillating is 2 meters long. Okay, that's the part that's setting up the resonance. Okay, now, if I want to find the frequency of the standing wave pattern we found over here in part D, well, first of all, which resonance is it? Which harmonic is that? If this is the first harmonic, what's that one going to be? The third harmonic. So I'm looking for the third harmonic frequency. What I want to do is I want to use this equation here. If I can find lambda 3, I can find, I know the wave speed is 150. If I can find this lambda 3, I can find the third harmonic frequency. Okay, so let's use this formula over here. I have 3 half footballs, and I multiply that by lambda over 2, and that's going to equal the length of this string, which is 2 meters. And that gives me a lambda of 8/3 meters. See if your neighbor followed that, what I just did there. Yes, sir. I did not. The length of the string or wire, whatever it is 3 meters. But the length that's vibrating is just the 2 meters on top. There's a 1 meter length that's hanging over the side. It's doing nothing except for supporting the block. Okay?
Doing this
Now, folks, why did I have to use 3 meters up here when I was calculating the mu? Because they gave me the mass of all 3 meters. And I just wanted to know how much mass there was in 1 meter. So I had to divide by all 3. But when we come to the oscillation, the part that's oscillating, the part that is the resonance, is the 2 meter length of string. Okay? Now, if I plug into this formula over here, 150 meters per second is equal to F3 times 8/3 meters. And if I solve that for F3, what I get there is 56¼ hertz. And this is the 3rd harmonic, or the 3rd resonance. Check with your neighbor. Check that your neighbor's on the bus. Yes.
I can't remember how that works.
Oh, why is it the 3rd harmonic? If the ends are different, the even harmonics are always missing. And so I go from 1 to 3 to 5 to 7 to 9. And if I look at this, I have half a football here. I have 3 half footballs there. I tripled the number of footballs that fit in the same 2 meter space. That means the wavelength has to get 1/3 as big, which means the frequency is going to get 3 times as big. If I did the same calculation and found that what the frequency was for this resonance over on the left, it would be 1/3 of that number. 1/3 of that number. Okay? Okay. Let's try another one. Try this one real quick. We have a length of string that's 60 centimeters long, vibrating in such a way that there are 2 additional nodes between the fixed endpoints. Whoa, that sounds familiar. That sounds like where we've just been at the beginning of the class. Okay, so that picture is still valid there. If the frequency of vibrations is now 1,000 hertz, what speed would the individual pulses of the string travel on the string? So this is not true anymore, but the picture is still true. Oh, thank you, Sam. So what I'm told is that this frequency is 1,000 hertz. Now we happen to know, because we've been here before, that that's the 3rd harmonic frequency. And we're told that this distance here is 60 centimeters. Well, I know that the wave speed is just going to be the frequency times the wavelength. And folks, this formula works for the 1st harmonic, for the 2nd harmonic, for the 3rd harmonic, forever. Every harmonic it works for. And we get the same value for V. Okay? So let's go back and do it for the 3rd harmonic. Well, I'm told that the 3rd harmonic has a frequency of 1,000 hertz. If I knew what this wavelength was, I'd be home free. Well, a wavelength is just 2 footballs, and 2 footballs would be 40 centimeters. Well, maybe I can see that, maybe I can't, Greg, but I can always use this formula. The number of footballs times lambda over 2 is equal to L. Well, if this is 3 footballs, times lambda over 2 is equal to 60 centimeters. That's going to give me a lambda equal to, I multiply both sides by 2, that's 120 centimeters. I divide by 3, and I get 40 centimeters. So this formula is one of the most important formulas that you will have in your toolbox. You can solve everything with this formula and this formula. This isn't like your anatomy class where you've got to memorize all 12 bones of the body. They're just two formulas, okay? Two formulas. Okay, so let's plug this in. If I want my answer in meters per second, I better put this wavelength into meters. And so that's going to be 0.4 meters. And that's going to give me 400 meters per second. A hertz is just a per second. Okay. Everyone feeling okay about that one? Okay, let's do another one. If you'll turn your page over. You know, there wasn't a whole lot of good that came out of that pandemic, but I got me a really good document camera out of the whole thing, and that's this one here. So let me put the screen down again. We've got enough time to do this. In this problem, a 50-kilogram block is being held by a wire to the ceiling. And we know the mass of the wire, but we don't know the length of that wire. We're asked to draw the fifth harmonic, the fifth resonance. And what kind of system is this going to be? Are the ends the same or different? Shout it out. Same, yeah. I've got a node at both ends. I've got a node here and a node here. Now, when you start with ends the same, you start with a fundamental frequency that has one football. And every time you go to the next allowed resonance, you add a football. So this one's going to have 5 footballs. 1, 2, 3, 4, 5. And all those footballs would be exactly the same length. You know I can't draw, right? Okay. Now we're told that the wavelength for the fifth harmonic, we're told it's 0.8 meters. Okay. Now what we're looking for is the mass density of the wire. That's the mu. Well, that's just going to be the mass of the wire divided by the length of the wire. Well, the mass of the wire is given as 0.1 kilograms, but I need the length of the wire. In the last problem, we had the length of the string, and we used that to find the wavelength. Well, now we're going to use that football equation in reverse. We're going to say the number of footballs times lambda over 2 is equal to the length of the wire. Well, I have 5 footballs. The length of this fifth harmonic is 0.8 meters. And that's going to give me the length of the wire. And 0.8 over 2 is 0.4. 0.4 times 5 is 2 meters. And so now if I put the length of the wire as 2 meters, I get a mu value of 0.05 kilograms per meter. And now we're asked to find the frequency of the fifth harmonic? Well, I know that this formula, the other important one, works for all the harmonics. And so if I knew what the speed was, I know what lambda 5 is, that's 0.8. I could find that fifth harmonic. Well, I can find the speed. This is a transverse wave. That's going to be the square root of the tension in the wire divided by the mass density. Well, the tension in the wire, if this is 50 kilograms, the weight's going to be 500 newtons, and that's also going to be the tension in that wire. So that's going to be 500 newtons. I divide that by 0.05 kilogram per meter. And when I take the square root, I get 100 meters per second. So if I plug that up into here, I get 100 meters per second is equal to F5 times 0.8 meters. Everyone see where I got? Oh, you can't see it. That's the V. That's the lambda 5. And I'm looking for the frequency 5. And that's going to give me 100 meters per second divided by 0.8 meters is equal to 125 per second. We call that a hertz. Oscillations per second are hertz. Okay, questions? Yes. Yes, we can think of it as a quasi node, and so the tension's about equal to the weight. Whenever it's a node, it's a V. Whenever it's not moving very much, you call it a node.
I get it.